Today's topic of discussion is interface electronics for MEMS. In last few lectures, we have discussed on MEMS devices, particularly micro machine, microsensors, and one of the basic job of micromechanical system is that it is a combination of sensors, actuators and signal conditioning circuits. So, if we do not think of the signal conditioning and signal processing circuits, then the system is or micromechanical system configuration is not complete. So, we have to see what are the various aspects of the output signals coming from the transducers and how do we proceed with those signals before processing, and after processing how those signals are fed to actuators for further functionalization or for further action. Thus, the interface electronics is an important aspect of any of the microsystem, and at the moment lot of work is going on this important topic, which is interface electronics. Now, the signal which is received at the output of the microsensors are of particular characteristics. Because of the different nature of the signal obtained at the output of the microsensors, its signal conditioning circuits and will be different. And in most of the cases, the signal processing part we prefer to have digital component, digital signal, and we are inclined or we love to process the signal using microprocessor or microcontroller or in a computer. So, there you know the only signal which is digital that can be processed, but sensors signals are not digital in nature. So, that is the reason we have to go for some conversion also. After getting the signal from the output of the microsensor, it has the condition, and then you have to change the analog to digital before further processing with the help of either microcontroller or microprocessor, and the output are taken, and then they will control the actuators and other things. In fact, this particular area is not widely explored till now, although the microsensor has reached a certain level at the moment, but signal conditioning circuit is not yet fully matured. So, what are the problems? Those we will highlight now, and we will try to solve some of the problems. Here the slide you can see the trends of the sensor electronics. We know the sensing element means microsensors are miniaturized day by day, and at present due to the micro miniaturization the sensor signal output level is very small. It is in the range of microvolt or millivolt, or if it is output is current, then some cases microampere, nanoampere, and in some cases picoampere also. If it is a capacitive, the change is in the range of the picofarads. So, since the change is negligibly small, so obviously there is a problem of the sensitivity, because if the signal output from the microsensors are extremely low, so it is very difficult the person to distinguish between the which is the signal and which is the noise, because any of the system will have noise, fluctuations, and those noises coming from different reasons, maybe the device noise, maybe the thermal noise, maybe the electromagnetic interaction noise. So, different kinds of noises are there, and we know the noise signals are also small in amplitude. So, because of that you need a very high sensitive circuit, so that you can extract the signal which is basically coming due to the input variation of the sensors, and you are not interested with the noise. That is one of the major problem of the signal conditioning of microsensor. Second is, day by day the functionality are getting more and more complex. We demand for increased functionality because we think it should be smart. If a microsystem is smart, if a microsensor is smart, then its functionality will be more and more. And because of the demand for increased functionality, lot of other things are coming into the picture, namely AD conversion, analog to digital conversion, because we love to process the signal at the end in digitally. Second is self test and auto calibration. Self test in auto calibration means many of the microsystem they need auto calibration, because with time the calibration may change because of the drift or other reasons. So, in that we want your device should be calibrated automatically. Self test. So, those are the added functions which were not there at the beginning, and if we want to incorporate those aspects into the microsystem, so obviously the electronics parts become more and more complex, and the sensor addressing. This is another point, because if you use multiple sensors for different activity in a microsystem, microsystem does not contain only one sensor, maybe multiples of sensors of various kinds are attached with the system at different locations. So, you have to address the proper sensor at the proper time. So, that is another question which we have to address, because in a multifunction multiple sensors you have to address proper kind of sensor in proper time. That is done only with the help of electronics. So, that also is a part of interface electronics. So, because of all those demands, gradually the miniaturization and the increased functionality are complexing the complete situation. And lastly, people are now thinking of SoC. What is that? System on chip. On a single chip they want the complete system, either hybrid or in monolithic version. There are two kinds of SoC, one is known as hybrid SoC and other is known as monolithic SoC. The whole system, if you want to have a small chip, so obviously complexity will increase further. So, the trends of the recent sensor electronics has made the interface electronics more complicated. That is why in many of the systems, many of the sensors we found that this particular part, the interface part is still in many cases it is a foggy area. There is not clear picture available and work is going on. In some cases we have identified some of the solutions, and in some cases we are yet to identify the solutions. Now, in this slide you can see some of the pictures also, that is system on chip SoC. There MEMS sensor built on one chip, electronics built on the second chip. This is one possibility. Electronics part you built on the second chip and MEMS sensor you built on the separate chip. Now, what you can do, both the chips, the MEMS sensors and electronics, both you can integrate together. That is known as the multiple module or MCM, or it is also some kind of SoC mounted and packaged in multi-chip module, which is known as MCM, or separately on PCB. Both the pictures are shown, both are hybrid. So, in the right side what we can see is this is the basically the multi-chip module. One chip is the sensor chip and the other is the electronics part. The sensor and electronics part, they are coupled inside the chip. So, it is basically system on chip, but it is multiple module. And other one is known as the hybrid mode. There the sensor part is here, for example, this is one accelerometer, and others are the different components which are connected in on a PCB to get the interface electronic circuit. So, this kind of things are known as hybrid, complete hybrid mode on a PCB. But people prefers this MCM package, which is much more miniaturized, and there you can get much more precision, because you know, if you go for hybrid for simplification of the technology or simplification of getting the package, but the problems are manifold, particularly as at the beginning I mentioned, people are much more cautious on the noise part, and some of the noise pickup will be coming from the parasitics, and in a hybrid package mode lot of parasitics will be there which are not directly seen. Some are visible and some are not visible. So, because of those things, so some other pickups will be there which may confuse your actual signal which is coming from the microsensor. So, if you go for a real multi-chip module, then technology is little bit tougher than hybrid on PCB. But if you go for SoC, real SoC on monolithic is still much more difficult. And then one of the problem lies there is the technology should be highly compatible, your MEMS technology should be highly compatible with the VLSI technology, because you are integrating your micromachining and microsensor fabrication steps along with the VLSI processing. So, there some of the restrictions are mainly you cannot go for long time etching, that is which is required in case of bulk micromachining. Mostly you have to go for surface micromachining, and there again you have to see the complete process steps which will not deter the other part also. So, that is why the complete monolithic version of the system on chip still now is occupied by few companies, and in majority of the foundry houses or majority of the chips are coming which is the SoC, but it is in a hybrid form, either on a PCB or in MCM. Mostly it is MCM. Okay. Now, hybrid system on chip, one thing here you can see, as I told you, the here both the pictures are the either MCM or system on PCB, but the next diagram which you can see here is basically it is the system on chip which are interconnected the sensor and the circuit monolithically. And here both actuators, not only sensor, is microsystem you will take, because it is known as system. System is, it may be included the actuator part also, sensor, circuits and actuators, both are integrated in this particular, and a pressure sensor prototype is shown here, that is the real monolithic version of SoC. Now, people are also concerned regarding the small cost overhead for added electronics. That is one issue, because if you add electronics unnecessarily, if you increase the cost, so you will not get the good market. Second is less effects for interface parasitics. This is also another concern. You should go for certain things which is free from the interface parasitics elements. And thirdly, flip chip monolithic integration bonding, that is another concern. If you have both integrated either monolithic or hybrid, you have to look into the bonding and integration part also, because packaging and bonding part takes the major share of the cost of any of the chip. So, that is why if the bonding and packaging part is much more expensive, if you go for miniaturization or monolithically the SoC is made monolithically, then you have to think before you go actually from the cost calculation point of view. Now, these are the issues which one should address before going for the system on chip. Now, let us come to sensor circuit integration. What are there in sensor circuit integration? There, first the sensor will be there, then signal conditioning circuit, and which is just after immediate after the sensor, then you will get the analog data, and this analog data must fade into the ADC, which will give you the digital output, and this digital data now you can safely process in a microprocessor along with RAMs and ROMs will be there, and then you can have some computer, you can have lot of control data buses from which you can feed the data to other subsequent module, or it can it can go to any of the actuators for controlling purpose. So, this is basically the complete picture where you have several blocks. First one is analog front end, which is the first block is the analog front end, then is analog to digital converters, the ADC, then comes digital signal processing. You can connect directly here a DSP chip also for further processing your signal, and then another electronics block will be there for controlling part also. That is basically maybe some actuation of the system which you want to do. So, these are the three pieces. Out of the three pieces, the first piece is the analog front end. So, the analog front end, lot of things are going on. Now, I mentioned that the demand of the people are going high day by day. So, that is why the sensor circuit integration is evolving new dimension day by day. That is why the lot of blocks are coming which are known as third generation, fourth generation, fifth and sixth generation, the sensor circuit integration. Basically, what are those? If you look into this picture, then it will be clear. You can see here in the third generation, basically we start from the first, second we are not talking about. That is the bulk edge, the heavy sensors and heavy circuits, and they are connected by wires in a hybrid mode, something like that. That we are not bothered at this moment in the MEMS and microsystem era. So, in the third generation, where you can see the transducers and signal conditioning, nothing else in the first block, and the one way analog, there is no two-way business here. Then it comes to ADC and then microcomputer, which is connected to RAM or ROM, and then it is a computer and data bus, which is basically the third generation diagram is shown in the earlier slide, same as the earlier slide. Now, in the second generation, from third generation to fourth generation, what are the modification? You can see here in the fourth generation, people like to have both way interaction in the analog. You see here from the microcomputer, when ADC is put in the microcomputer, there also some part of the signal is coming at the integrated sensors, that means the analog front end here. Here also you can see transducer, then signal processing, not signal conditioning. This is the difference. First one is signal conditioning, then second diagram, which is fourth generation, this is a signal processing. Signal processing means all these blocks are included here. So, then it will have IO inputs also. From the IO inputs, so basically from there is a direct interaction between your microcomputer again. So, that means this is the fourth generation where you have the access of putting the output or some of the signal from the microcomputer back to the front end circuit. Obviously, if you add this to the front end, with the sensor input signal it has to be converted into again analog. So, that is not shown here, some IO is shown, but next part is the 4th generation to 5th and 6th generation the sensor circuit integration. Here you can see the first module has been changed completely. So, there they are not only integrating transducer, but transducer arrays, not a single sensor, array of transducers. Then here coming into picture sensor addressing. So, that part will be there, ADC is there, microcomputer is there, PROM is there. That means what is there in the 4th generation, whole thing came into one module, and that is the integrated sensor, which itself is smart. Then again bidirectional sensor bus is there, and there the communication will be there with again computer, and from this computer it goes to the host computer. So, that means it is further refined, and since in the first block all the blocks in the first 3rd and 4th generation are integrated. So, the chip of the 5th and 6th generation, the front end will be much more complicated, and it will be highly expensive also and challenging to get this kind of the conditioning or the interface electronic circuits. Okay. Now, role of interface electronics with integrated MEMS sensor. As I told you, there are a lot of characteristics of the signal received from the output of the microsensors. What are those characteristics, and what are the challenges, so that you can go ahead with your signal conditioning or interface electronic circuit. Number one is that the output is microvolt range out, because it is not written in the microfarad or micro ampere or picoampere. Actually, for processing, whatever the signal output we get from the microsensor, we can convert into a voltage. So, that will be very easy for further processing. That is why it is written only in the microvolt range. So, output of the sensors are always in the microvolt range, and those sensor, the problem if it is a microvolt, then what are the challenge? Low offset and noise. So, offset will be there, that will be again in many of the sensor it is a microvolt range, and noise, that also in the microvolt range. So, if both are noise, offset and your basic signals are microvolt range, then this is the problems, how to tackle that. These are system characteristics of voltage level signals output, that is as I mentioned, people always prefer to have voltage levels rather than the current signals or some change of capacitance or change of resistance. Ultimately, we convert into the change of voltage. Next is the parts per million change, ppm changes, micro ohm or femtofarad. So, changes with the input variation of the measurand will be in the range of ppm level in many cases, and that ppm level change has to be reflected at the output. So, people prefer for that on chip analog interface, not the ppm level change. If it is taking the sensor and with the wire, if you connect with your amplifier or other things, then the problem comes is again. So, you cannot see the effect of ppm changes. So, you need on chip analog electronics, and system should have amplifier and buffer outputs. Okay, amplified and buffer output should be there. Next one is analog signals. Then these are the characteristics analog. All the signals mainly received from your output of the microsensors are analog in nature. In module ADC is required, but characteristics ultimately for processing should be digital signal. That is why we are connecting ADC. Cross parameter sensitivities is another major issue. Cross parameter sensitivity means your sensors is intended to sense the variation of the measurand at the output, at the input, which will be reflected at the output. But your intended measurand, there are some secondary effect which can change your output of the sensor also. For example, a sensor in case of piezo resistance, say pressure sensor, the piezo resistance can change with pressure, that is the intended variation, but this piezo resistance can change with temperature, there is a secondary effect, that is known as the cross parameter sensitivity. Your sensor should not be highly sensitive with the temperature variation, although it is there. You have to take care at the circuit level, so that the secondary parameter variation is not reflected at the output of the sensor. So, that is the cross parameter sensitivities. Sensing of secondary variables, how can you check it? You have to sense the secondary variables, and the secondary variables should be minimized or should be deleted at the output of the complete front end analog system. Now, pure parameter measure, you should get the actual value of the pure parameter which you are looking for. Now, individual device outputs. So, in case of multiple sensors connecting, so you are interested in individual device output in a system. So, there may be lot of sensors with different nature. So, they should not be cross connected, cross related. One sensor output cannot be interrupted by the other sensor output. That is why individual device output should be separately sensed. Embedded microcontroller is some of the solution, but is a real challenge to have. Multiplex and addressable. So, that is another issue where you are working with is a multifunction sensors in a microsystem. Next is coming offset, slope and linearity problem. These are the inbuilt problem of any kind of sensor. Offset will be there, linearity is not, is although it is a desirable property of any sensor, but all the sensors will have some non-linearity. So, that how to get rid of that problem, and for that you have to have compensation standards should be there, and people prefer for compensation digitally. Output drifts over time, that is another thing. Last one is output drifts over time. So, that is the sensor drifting that we know with time because of the aging. So, the calibration of the sensor may change and the output may be drifted, may be changed. So, to reduce that change or the aging problem, compensation can be done with the help of stable references in module actuators. Self-testing remote calibration. So, that is because some of the sensors which are already fixed and which you do not have access directly. So, how can you correct them? So, that is why people are thinking the testing of the sensors will be done automatically and remotely. Remotely it can be calibrated also. So, that means these are 5th and 6th generation the microsystem sensor circuits, which are really challenging task, but people are working for it. Obviously, solutions are coming and will come in future. Now, sensor signal conditioning, which are we talk about, this is analog front end. So, analog front end, the input and outputs, that is the first block, their low signal amplitude, low frequency noise and cross parameter sensitivity. These are the input, there are 3 issues we have to remove. Output we need what? High voltage output for subsequent ADC, appreciable signal to noise ratio, cross parameter stability. These are our requirement. By inputs are problematic because they contain the low amplitude signal, low frequency noise. So, this is one of the important aspect of any of the sensor signals. So, in the low frequency noise are included into the sensor actual signal, and how to get rid of that. So, there the inputs are fed. First you have to do what you have to do? You have to pass the signal into an amplifier, because first you have to raise the signal level before further processing, and then what kind of amplifier we will choose, which will give you better low frequency noise as well as the drift. So, that you have to look for. So, that amplifier then goes to some ADC or some filter, and then ultimately it will go to DSP. Now, motivation on amplifiers. As the immediate block of any microsensors is amplifier, so what should be the motivation for selecting the amplifiers? Many sensors, particularly pressure sensor and accelerometer, output DC signals are in microvolt range. Signals are DC and microvolt, and these signals are best processed on chip. However, the offset of the basic IC amplifiers is also in the microvolt range, especially in CMOS. So, special techniques are required to reduce the offset of IC amplifiers. Okay. So, this is one first objective, to choose an amplifier which will have minimum offset. So, in that respect, we know the differential amplifier configuration is the best choice. So, for sensor amplifier, people prefer or widely use the differential amplifier, which can amplify DC signals also. So, why this structure is balanced? In all differential amplifiers are balanced structure, and circuit is shown here. This is a MOS differential amplifier. So, here normally since the structure is balanced, so it is offset free, it rejects common mode and power supply interference also, easily realized in both CMOS and bipolar. In a both technology, both CMOS and bipolar, you can make this kind of amplifiers easily. And how we get the offset? Offset is basically due to the component mismatch. Although it is a perfectly balanced structure in differential amplifier, but you have seen here M1, M2 and R1, R2, these are the components. The M1, M2 should be perfectly matched pair. If it is not matched, so obviously it is likely that you will get some offset also. So, in that case, this unmatching of the components is coming due to the process variation. Although in the design level both M1, M2 are perfectly matched, in simulation level also you can check it, it is perfectly matched, but in reality when you get the chip, if you test it, then there may be some mismatch, and because of that you are getting the offset, and that mismatch is the contribution of the process variation and the lithographic errors when you go for the photomasking. So, because of that, maybe in some level some of the area of the active devices, either the gate area or the oxide thickness on the gate, so those things may change a little bit due to the process variation, and because of which you can get some offsets. In case of bipolar, this offset voltage is nearly of the order of 0.1 millivolt, but in case of CMOS it is much worse, near 10 to 100 times in some cases compared to the bipolar devices, bipolar differential amplifier. Okay. So, these are some of the points when you address this low offset, you should think not only in the design, but also in the process side of the VLSI technology steps. Now comes drift. So, that is offset which I talked about. Now the drift. Drift is basically due to temperature, aging and packaging stress cause time varying offset. So, the package which are used, if stress is generated, because as I told you in the last lecture when bonding and packaging class, so there because the various layers are bonded together, so there is a probability of stress on the active elements on the devices because of the mismatch of the thermal expansion coefficients and other parameters. So that can, because if there is a stress and that will be reflected in your device, and for that you can get some change of the signals which is known as the aging or temperature drift. And how can you reduce that? You can trim. In case of bipolar, there are different, the associated components are there, they can be trimmed, and according to the external trimming can change the can compensate the drift and offsets also, but it is very difficult to to adopt that technique in case of MOSFET. Third problem is flicker noise. Flicker noise is basically the 1 by f noise which is coming in the low frequency arena, and there one has to check how the 1 by f noise or flicker noise should be controlled, how it can be controlled. MOSFETs are worse than bipolar transistors in case of the flicker noise also, varies inversely with transistor area, this flicker noise. Now this diagram shows the two noise, how it varies with frequency and what are their magnitude. The diagram here you can see it is plot is the frequency versus the noise voltage, both are in logarithm scale. Now you can see at very low frequency 1 by f noise is very high, noise voltage is very high, and if you go on increasing the frequency it reduces, and after that you are getting the thermal noise, and this thermal noise VTH is frequency independent, but flicker noise is completely frequency dependent. Now because of the thermal noise, the VTH you are generating, that may also give you is a constant drift. So the amplifier behavior at low frequency is characterized by offset, drift, 1 by f noise, CMRR and PSRR. So these are the parameters which has to be properly adjusted, and proper measures is to be taken when you are designing those sensor interface electronic circuit, particularly amplifier. Then what is the solutions? Offset and 1 by f noise are part of design, but we can reduce offset enough by using large device and good layout. Those are one of the option. Second option is trimming, particularly it is possible in bipolar or by DOC, which is a dynamic offset cancellation techniques. This is one of the techniques which is nowadays used in many of the sensor signal conditioning circuits. DOC, dynamic offset cancellation techniques. DOC techniques also reduce 1 by f noise, not only the offset, both offset and 1 by f noise both are drastically reduced by dynamic offset cancellation techniques, which can be used either MOS or bipolar in both cases. Now trimming. For the trimming, what you need? You need an external potentiometer. What are the plus points and minus points of the trimming techniques to adjust offsets and other parameters, undesirable parameters basically. Here you have to have an extra component and extra pins in IC technology, which people do not want. If extra complexity is coming, extra component means they go for sometimes laser trimming. Laser trimming of the components are also available, that technique, sometimes they use that. But other trimming possibilities are component switching. Those are basically Zener zapping, fusible links and PROM. PROM and fusible links are basically used in many cases. Those are because there are a lot of links connected with different components. So if you want to fuse those links, that means fuse and anti-fuse technology, for that you have to program it. So something is increasing, so you can make your circuit in such a fashion by fusing some of the links, you can disconnect that component. So you can basically it is some kind of trimming. That trimming is not done by potentiometer, that is not done by laser, but you can done by switching mechanism, and that is one of the preferred techniques in nowadays in many of the sensor interface electronic circuits. You can trim the component to reduce offset as well as the drift by switching technique, and that is the fusible links technique. You can disconnect or you can connect also, that is known as fuse and anti-fuse technology. So there also you can easily connect some of the resistance with some polysilicon links or polysilicon fuse, and those fuses can be blown any times by using some using some signal of high current pulse. Okay. So that technique is also preferred technique for those cases. Now DOC techniques, dynamic offset cancellation technique. So that techniques are auto zeroing. You need their sample data, you have to sample the offset, and then you have to sub. These are the technique. One is the auto zeroing technique, and there you need data is to be sampled, and you sample the offset signal also, then you subtract it. So for that case you have to chop. Chopping is included there. Continuous time processing, modulate the offset and away from DC. So offset signal you modulate it, then you take it away from DC, and then you can subtract it, and then you can get rid of those things. This is dynamically done in the complete processor. Obviously it needs some switches, and those switches are either CMOS or BiCMOS, because CMOS BiCMOS, one of the biggest advantage is a low power and highly integrable. So that is one of the driving force behind those two techniques. Now DOC techniques versus trimming, if you compare, then the DOC techniques can reduce offset and 1/f noise simultaneously. It has got excellent long term stability, no additional cost for testing. So this is the plus points of the DOC technique. On the other hand, the problems are here: reduced bandwidth, increased circuit complexity, because you need lot of blocks there, you have to integrate monolithically. So increased circuit complexity, aliasing and intermodulation issues, those are also required in case of the dynamic offset cancellation technique. In brief, I will just give you some picture on the auto zeroing techniques and DOC, means the chopper stabilization techniques. So auto zero technique here, basically the input is coming here, there are 3 switches used, S1, S3 and S2, and this is an ideal amplifier. So what there, this is basically the offset signal is coming here. So now initially you can connect the switches 1 and 2, this switch 5 and this is another 5, this switch S2 you connect it. Now there are no inputs are there, whatever the offset because of the mismatch of the amplifier etc. is coming. So those things are, the offset is amplified and that is again stored into the CAZ, this capacitance, you can store it here. In the next step you can just put the input signal and connect it there, and you can subtract it, and automatically in this way you can get rid of, because output signal is something like that. So offset is going to be reduced and automatically is going close to 0. So this technique is used in many cases, auto zero technique. The residual of the offset which is at the end available, which will be reduced by the amplifier A, which is the amplifier gain. Now this residual offset in auto-zero technique is determined by three parameters. One is charge injection, how the capacitance is made, CAZ, how you can charge the capacitance, leakage on capacitor, leakage should be as small as possible so that total offset can be stored there initially, limited amplifier gain and bandwidth. These are the determining factors in this auto-zero technique. Practically CAZ is a large, sometimes in order to have the three parameters which are intended, large charge injection, leakage, low leakage, and for that you may require CAZ very large value, and if it is a very large, obviously it cannot be monolithically integrated. You have to get it outside your chip, external. Multi-stage amplifier topologies sometimes is used, and here FC is larger than Fs. Fs is the sampling frequency. A residual offset of 1 to 100 microvolt is sometimes reported. Now, in auto-zero technique, the noise picture looks like this. Here you can see, without the low frequency noise cancellation techniques, which is auto-zero, the frequency 1f noise are like that, but after that you can see here this 1 by f noise has been reduced to this particular point, and here is the one frequency point fk, which is known as 1 by f noise corner frequency, and here the thermal noise is as it is like VTH, but the other noise at the low other means basically the 1 by f noise, flicker noise, and that flicker noise is Fc by Fs into VTH and is constant up to that 1 by f corner frequency. So, that means some improvement we get it in case of auto-zero technique. Now, another technique which is used normally, which is known as a chopper stabilized amplifier. So, chopper stabilized amplifier is one of the preferred technique and people use it, although it is little bit complex and difficult compared to auto-zero. Here the building blocks of the circuit are more, and here signals are first modulated, then it is amplified and again demodulated, and you can see here this is the input, and here you are modulating the signal, and V input looks like here, and then after modulating the V1 signal is shown here. Here you can the signal as well as some noise are shown here, and then this is the block where you can the offset and Vn both are added here, and after that the modulated signal and addition of VOS, which is offset and noise signal, is fed to an amplifier, and then the output is again coming to another modulator, which is basically works for demodulator, then low pass filter, and you are getting the low frequency signal output here, where the other parts of the noise due to the offset and the offset error and other flicker noise parts are removed from the output. Now, here the output signal are continuously we are getting without that flicker noise and offset, but here the problem is you have to have one addition filter, which is low pass filter, you have to connect at the output. Now, this is a chopper stabilization techniques is shown here. Here is a basically the wave in terms of the waveform, this is the V in, same as earlier diagram, little bit elaborate the waveforms. Here is after modulation, you will get the waveforms looks like that, then noise and offset is separated, the VOS and Vn, this you are adding here, then your preamplifier after that VA will be here, because this thing and this thing are added at the amplifier output. Now, this VA is fed here, and after the second modulation that is done here, and the second modulation, and you can get the signal which looks like this, then low pass filtering out, then you are getting the V output here. So, this is the complete the flow of the chopper stabilization technique, CHS technique. Now, chopping is done in the time domain. So, how it is working is again explained in this diagram. So, here is the V input is because I told you the signal is almost DC. So, it is shown here, this is from 0 level to this signal level here. Now, the V chopper, that is basically some digital signal is added, the V chopper, when it is coming here, then we are getting V1 where the offset is here and this is mixed with that in the modulation technique. So, after that you are getting the amplifier, then after amplification the output is looks like that, the red line is offset and this signal which is V chopper is connecting together along with the signal. Now, what is going on again at the V output, the V chopper is again fed into that the second modulation scheme, and after that this signal and this signal are added together at the V3, and if you use the low pass filter, then you can see the output which is offset is comes to almost 0 level and the desired signal has been amplified and which is separated out. So, that is the chopping in the time domain, the how V in, V1, V2, V3 and V out looks like at different stages, it is shown here. Now, here in this particular case, in the chopper stabilized amplifier gives you the output, you can see here that offset which is basically thermal noise gives you the steady offset, and that offset has brought down to 0, but at the low frequency noise has some thermal voltage at the low frequency, and after that this technique completely removes the drift or the offset arises due to thermal noise. So, here 1 by F noise is completely removed provided F chopper is large compared to 1 by F corner frequency, that is one of the condition, significantly better than auto zero technique. That is clear from the noise response curve in case of auto zero technique in the and also the chopper stabilization technique. So, offset of few microvolt, charge injection of the input modulator, because of that input spikes are there and this come because of the bias current is of the order of picoampere. Now, some of the circuits which I mentioned earlier in case of my lecture on accelerometer, I am repeating here since it is a I am discussing now the interface electronics. One of the parameters is the temperature drift that should be minimized, and they are done with the help of certain circuits which is NIC technique. Okay. So, this NIC technique which is basically the negative impedance converter, NIC. So, this negative impedance converter, there some resistance is connected which is RT R1 by R2 by this circuit. If some positive resistance change is there due to temperature, the total RB, then that will be compensated by another resistance which is minus Rn. What is increasing here, that will be compensated by reducing that. So, in a different circuit technique which is connected at the Wheaton's bridge output, so that the whole thing will be temperature compensated at the bridge level. So, in temperature increase, the bridge resistance decreases and bridge sensitivity also will reduce. If we made the IB, this current, bias current, IB to depend inversely on bridge resistance RB, RB is the total bridge resistance, the output voltage becomes temperature insensitive. That is our job. The IB should depend inversely on bridge total bridge resistance RB. So, that is done with the help of the impedance converter, and that detailed circuit diagram is shown here. It implements a negative resistance minus Rn as shown in earlier diagram in series with the RB. RB is the total resistance of the bridge, such that if IB increase with temperature, the Rn is equal to RT into R1 by R2, and RT can be adjusted externally with some potentiometer or some other pot. So, now this is some chip in that direction, temperature compensation chips are also available, ready made chips which is maximum 1457, and which gives you 0.1% accurate signal conditioner circuit chip for piezoresistor resistive sensor compensation. This chip configuration is shown here, and its detailed characteristics of Maxim 1457 is also mentioned in this diagram, which reveals that it is a very good chip for piezoresistive sensors, and it can go -40 to +125 without any problem. So, that temperature variation has been compensated inside the chip itself. Now, these are some of the simple circuits which can give you some offset cancellation also. That is, the bridge output is connected with 4 resistance R1, R2, R3, R4, and by adjusting these 4 resistances, the offset voltage can be drastically reduced, and that technique we have used in our case in our accelerometer. And here the circuits, this TC 7652 is basically a chopper stabilized amplifier, which has got advantage also in case of the offset cancellation 1/f noise cancellation, and along with that we have used 4 resistances to further reduce the offset value, and that in a PCB package we have made along with the accelerometer. Both this and this one are accelerometer on different packages, and the circuit is the same, and there we can get rid of the offset value drastically. You can, if you look on the 2 curves, you can see bridge offset has been balanced using the shunt resistances, which are R1, R2, R3, R4 as mentioned in earlier diagram, and offset voltage was reduced from 450 millivolt to -10 millivolt only for a supply voltage variation to 1 to 15 volt. With that supply voltage variation, you can reduce, initially it was 450 and it has reduced to 10 millivolt only. So, now with that, let me conclude the sensor bridge which we have developed in our laboratory. We have come to a certain hybrid mode interface circuit, which is also giving good result so far as offset is concerned, but temperature compensation is not that much perfect. So, this bridge which we used for our circuit provide differential low frequency less than 100 hertz, low amplitude less than 20 millivolt signal, which is to be amplified, and in that case this amplification has been done up to 6.5 volt in chopper stabilized amplifier with R1, R2 or 1 kilo ohm and R3 or R4 with 500 kilo ohm, and the TC 7652 configuration provides a stable output up to 200 hertz. So, this is basically some small example which you are doing here, but that is not the final. You have to design separate blocks using your required chopper stabilization techniques, amplifiers and all other things, if you want to have monolithic interface electronic chip for any kind of sensors. So, there is work going on nowadays for universal interface electronics. So, the interface electronic chip can be connected to any kind of sensor, either it is a piezoresistive or piezocapacitive or maybe other kind of sensor. So, these are the 3 things we have discussed today. So, let me stop here. Thank you very much.